I welcome all the students. So today we are going to learn the topic or the point of the discussion is B-spline curve. Okay, so we have covered already in all previous sessions or the lecture up to the Bezier curve. We have started learning the two important curves. Okay, one is Bezier curve that we have covered, and now today we are going to learn the in detail what is the description of the B-spline curve, as well as we are considering, as we have learned the Bezier curve, okay, it is possible for us to have a differentiate between Bezier curve and B-spline curve. Okay, so our today's topic of discussion is B-spline curves. Okay, so I'm just moving to the next slide to start with the discussion of the B-spline curve. So the first point that we are going to understand or going to consider about the B-spline curves and the surfaces. Okay, so we are considering here B-spline curves and the surfaces. Okay, now these B-spline curves and surfaces, there are most widely used. Okay, these are widely used class of the approximating splines. Okay, so there are, we can say, some disadvantages of the Bezier curve. Okay, we want to cover it. Okay, or another type of the curve we use with the help of the B-spline curve. Okay, so these are B-spline curves and surfaces are most widely used class of the approximating splines. Okay, now as I told, we should compare the B-spline with the Bezier curve. Okay, so we have learned Bezier curve. So now we are going to consider the B-spline and Bezier curve. So B-spline are having two advantages over the Bezier curve or Bezier spline. Okay, it is having two advantages over the Bezier spline or Bezier curve. What is the first advantage? The first advantage is the degree of B-spline polynomial. The degree of B-spline polynomial can be set independently of the number of control points. Okay, so we have seen in the Bezier curve, the degree of polynomial depends upon the control point or the maximum. Suppose I'm having n control point, so it will be n minus 1. Okay, but here in B-spline curve, the degree of B-spline polynomial can be set which is independent of the number of control points. It is not depends upon the number of control points we are having. Okay, so this is considered to be the first advantage of the B-spline curve. Okay, now the second advantage that we are having is the B-spline curves allows the local control over the shape of the spline curves. Okay, so they are going to allow the local control. Okay, it can be added, so they allow the local control over the shape of a spline curve or the shape of the curve or the surface. Okay, so this is what we are considering the major two advantages. The first advantage is the degree of B-spline polynomial not depends upon the number of control points. Okay, so it is independent. Okay, and the second, we can say the B-spline allows the local control over the shape of the spline curves or the surfaces. So we can have the local control over the shape of the spline curve or the surfaces. Okay, so I consider these two are the main advantages of the B-spline curve over the Bezier spline or Bezier curve. Okay, now only the trade-off that we are having between the Bezier curve and the B-spline curve. The meaning of the trade-off here is, as it is having the two advantages over the Bezier curve, but we can say it is having this as a demerit or the drawback. We can say that the B-spline are more complex than the Bezier spline. Okay, so I can say the only drawback or the disadvantage or the difference that we are having, okay, as compare the B-spline with the Bezier curve, is that if I compare B-spline and Bezier, then B-spline curves are more complex as compared to the Bezier curve. So that is the only trade-off that we are having. Okay, suppose we want to have these advantages, I want to achieve these two advantages, or I want to seek or take these two advantages, okay, of the B-spline curve, then obviously there is a trade-off that we should accept the little bit complex or complex ability of the B-spline curve. Okay, so we have to accept the complexity of the B-spline curve. Okay, then we can achieve this two advantages, or we can get this two advantages of the B-spline curve. Okay, so this is what the basic related to what is B-spline curve and how I compare this B-spline curve with the Bezier curve. Okay, let us start understanding the B-spline curve in detail. Okay, now we can write general expression for the calculation of coordinate position along a B-spline curve in a blending function formulation. Okay, so we are considering now the blending function formula of the B-spline curve, as we have already considered for the Bezier curve. Okay, now we consider the blending function formula for the B-spline curve. Okay, so what this formula is, so let us look at the or understand the formula. So here the P of u, okay, function P of u is equal to, again it is a summation, okay, and having the values k is equal to 0 to k is equal to n. I think we have seen already such function for the Bezier curve. So it is a summation of pk. Okay, so all these position vectors, or we can say the control points, okay, summation of this, and I'm having it is multiplied with the blending function, and the blending function is b stand for here B-spline. I think we have used the Bezier as some another term that we are using, okay, bzk or something like we are using, so that it is differentiate between the Bezier and B-spline. So I'm having the summation of k is equal to n. So number of summation, I take the pk, all the position vectors for the point, and I'm having the function, blending function is b from k to d, k comma d, and the value is u. Okay, now here what is this u? So u varies from the u minimum value to u maximum value. So the u will varies from the minimum to maximum. And what about d? So here we are considering the value of d. Okay, so we are considering here the value of d will be equal to minimum value of d is we are considering it as a 2. Okay, so definitely we should have the start point and the end point. Okay, minimum 2 point that we are considering, so it will be minimum 2, it is less than or equal, means it is in between 2 to maximum n plus 1. Okay, to maximum n plus 1. Here we are considering n also indicate the number of control points and the thing that we are considered. Okay, so this is the B-spline blending function formula that is used by the B-spline curve. Okay, so now let us continue our discussion where the pk, okay, so this pk that we are considering, okay, are the input set of n plus 1 control points. So that is what I told. So I'm having the pk indicate the input set of n plus 1 control points, or the position of the position vector or the control point that we are considering. Now there are several differences between this B-spline formulation and that for the Bezier spline. Okay, so are several differences that we are having between the this particular equation that we are using for the B-spline and whatever the blending function we have seen for the Bezier spline. Okay, so Bezier spline or Bezier curve. Okay, let us understand which are the differences that we are having. The first we are having is the range of parameter u. Okay, so the range of this parameter u now depends upon how we choose the B-spline parameters. Okay, so the range of u will now depends upon how we are going to choose the B-spline parameters. Okay, second, and the B-spline blending function. Okay, so this is my B-spline blending function b k comma d. So this one, I'm talking about this particular function b at the value k comma d are polynomials of degree. So they are the polynomials of the degree d minus 1. Okay, where the parameter d can be chosen, to be an integer value in the range of 2. What is my parameter value or degree will be d minus 1. Okay, so I'm having the d value will be minimum 2. Okay, so I'm having the polynomial degree will be minimum 1. Okay, so d value should be from 2. Minimum value of d is 2 up to the number of control points that we are having. Just now we have listed it here. The number of control points will be n plus 1. Okay, so we are considering these are the two differences that we are having. So we are having one more difference, okay, up the this equation or blending function of the B-spline compared with the Bezier spline equation. Okay, so I'm having the next slide. I just put that one more difference, and then we can see, I think it is important for us to see how this B-spline curves will look like. Okay, so with the help of the diagram, so I'm just moving to the next slide to continue our discussion of the differences. We have seen here two differences that we are having. Okay, so let us move to the next slide. Yes, the third difference that we are considering here, okay, the local control. So that's why we have said that this is one of the advantage of the B-spline curve. Okay, so we can have the local control points, or local control for the B-spline is achieved by defining the blending function over sub intervals of the total range of U. Okay, so this is what the difference which is not there in the Bezier curve. Okay, Bezier curve not having the local control. Okay, but here we are having the local control for the B-spline, and that can be achieved by defining the blending function over the sub intervals of the total range of U. Okay, so I think with this discussion, let us have a diagram to understand the uh, thinking of related to the B-spline curve. Okay, now actually here, okay, I think we should not consider it as a Bezier curve now. Okay, I just considered. Okay, so this is not, we have Bezier curve. We are comparing with the Bezier curve, but these are our B-spline curves. Okay, I just mentioned it here. Okay, so this is my B-spline curve. Okay, not the Bezier curve. Okay, now the blending function for the B-spline curves are defined. Okay, the blending function of B-spline curves are defined by the Cox-de Boer recursive formulas. Okay, so here the B-spline curves are defined with the help of, or by the Cox-de Boer, okay, recursion formula. Let us understand what formula it is. Again, this is what the formula that we are having, which is defined by the Cox-de Boer recursion formula, which is used for the B-spline curve blending function. Okay, now just let us understand how it will see. So recursive function bk comma 1 bk comma 1 to u. Okay, so it is starting point, so it is starting with the one value, and here I'm having bk comma d up to d. Okay, and what is the d value we have seen? It will be minimum 2 to maximum n, okay, number of control point that we are having. Okay, so here the value of this function will be 1 if the u varies from, or if the u is having the range uk to uk plus 1. So if u is in the range uk to uk plus 1, then the value of this function will be 1, otherwise it is set to 0. Okay, and how I calculate for b spline blending function k, okay, with the input k comma d. Now here I'm considering it as minimum 1 is there, and here it is d. So value of d is minimum 2 to maximum n that we are having, n plus 1. So it is calculated as, so we are having the u minus uk divided by uk plus d minus 1 minus uk into bk. So I'm having the second function d minus 1 u, so that is what my function here I considered, plus I'm just adding the same formula. Here it is second next point. Okay, so we are having this as this is the initial point or the starting point, plus I'm having the point which is having the d value. Okay, so uk plus d minus u divided by uk plus d minus uk plus 1, again it is multiplied with the bk plus 1 into d minus 1 u. Okay, so this is the formula which is given or defined by the Cox-de Boer recursive formula, and that can be used for the B-spline function. Okay, now where we can say each blending function is defined over d subinterval. So that is what I have explained here. So we are considering here the d indicate I am having, which is d is my, I say as the local control, and it may define the d subintervals of the total range of u. Okay, so that is what we have achieved. Okay, so we are having the d sub intervals, minimum sub intervals will be 2 and maximum it will be n plus 1. The selected set of sub interval endpoints uj is referred as not vector. Okay, now the selected set of sub interval endpoints, suppose I consider I am having the two interval d is equal to 2, so then the u of j may be considered as a 2, so j value may be 2, is referred as the not vector. I think maybe in so many slides we are going to use this word, which is called as the not vector. Okay, so that not vector will be my the local control or local control point for the B-spline curve. Okay, we can choose any values for the subinterval endpoints. We can choose any values for the subinterval endpoint satisfying the relation, okay, which must satisfy the relation u of j less than or equal to u of j plus 1. Means if I'm having the second point as a subinterval, then it should be less than the j plus 1. So next point having should be have the next value. Okay, so that is we are considering. That is the relation uj should be less than u of j plus 1. Okay, now with this, let us understand the continue our discussion of the B-spline curve. Values for u minimum and u maximum. Values for u minimum and u maximum then depends upon, I think in the same previous case we have used this value as u minimum and u maximum. So here also we are considering it depends upon the number of control points we select, the value we choose for parameter d, and how we get the set of sub intervals or the not vectors. So on depending upon this that we are having this value, let us understand the things in detail with the help of the diagram. So we are considering here, it is not Bezier curve, we are talking or we are having the discussion with the B-spline curves. So we are considered the B-spline curve diagram. I want to be able to concentrate on the diagram to understand the B-spline curves. So the local modification of a B-spline curve, we are considering local modification of the B-spline curve, changing one of the control points in A. Changing one of the control points in A produces the curve B. So if I change one of the, so this is my original diagram A. If I change the control points, one of the control point, it produces the curve in the B. So this is A, and after changing I will get this value as a B, diagram B, which is modified only in the neighborhood of the altered control point. Only in the neighborhood of the altered control point. If I'm changing the neighboring control point, then how the change will occur in the curve. So that's why I want everyone to understand this. Now you see here, this is my first point, I'm starting point. This is my end point that I'm having. So now this is the first point, obviously I will get the curve something like this. Now this is my next point. Now you can find these 2 points are very close to each other, so I'm having, this is more closure equation. So this is my one point and this is the another point which is close to it. Again I'm having this and this, these 2 points are close to each other, so I'm having this particular shape. We have seen that if the 2 points are close to each other, then the curve will be pulled toward these points. So it will be pulled toward this. Then I'm having, this is the point and these are the point. So here in this case I'm having these 2 points which are close to each other. Here also I'm having the 2 points, control point, which are close to each other. Now in the diagram number B, in the second diagram of my B-spline curve, I'm just changing this control points, the position of the control point, that is what we have written. Changing one of the control point in A produces the curve B. Now here I am having these 2 points which are close to each other. See, now this point I have shifted over here. And another point, this point we have shifted at this particular position. So I have increased the gap of this. This is the local control. I call it as, with the help of the local control I have changed, and you can find this difference between the shape of this. Here I am having the different shape. Here I get the different shape, and the as per the tangent vector is also there. So this is change. Similarly, here also I am having these 2 points which are close to each other, but again we are just making this point as the same. As per this, we are not changing, so I will get this shape of as it is. So only the difference we have applied is here. Instead of that I am using the control point difference over here, and this is the change in the shape of the curve that we have achieved. So this is going to change the shape of my curve with the help of this diagram. So let us understand, this is what we can achieve just by changing the or alternating the neighborhood of the control point. If I am going to change these 2 points which are closer to each other, again the shape will be changed. As these 2 points are close, the curve is pulled. So curve is pulled at these 2 points. Here it is also pulled, but we have separated this. And now there is no pulling of the curve, but here they are, suppose again I change, definitely the shape will be changed. And this is what this diagram indicate us related to the B-spline curve. So with this discussion and understanding the shape of the B-spline curve, as well as how it is going to affect to the changing to the local control or changing the local points of this, and we have seen with the diagram, A diagram, and what is the difference between the B diagram. If I just change the neighborhood points and just changing their position, and the shape of the curve also changes. So this is what the clear diagram indicate the B-spline curve. Now with this, I think we need to understand now the very important thing, the properties of the B-spline curve. Okay, so let us understand the properties of the B-spline curve. Okay, so now we have to go through all the properties of the B-spline curve. Okay, let us understand these properties one by one. Okay, so every property is considered to be have compared with the Bezier curve. Okay, so let us consider what is the first property we are having. The polynomial curve has a degree d minus 1 and the c of d minus 2 continuity over the range of u. Okay, so we are having the polynomial curve has the degree d minus 1. Okay, so we are having the d value minimum 2, so I'm having the degree 1. If it is n, then accordingly we are going to do this, and it is having the continuity over the range of the u. So this is my first property of the Bezier curve. Okay, what is the second property of the Bezier curve? Second property is for n plus 1 control points. I'm having the number of control points are n plus 1. The curve is described with the n plus 1 blending function. So if I am having the n plus 1 control points, the curve is described with the n plus 1 blending function. Okay, so that is what we are having. So depending upon n values, suppose I'm having the n is equal to 3. Okay, then my number of control points will be n plus 1, which it is 4. Then the curve can be described with n plus 1 bending functions are possible. Okay, so I'm having the 4 different functions are possible. So definitely we are going to look the one more diagram for understanding of this also. Okay, let us move to the third property of the B-spline curve. Okay, what is the third property of B-spline curve is each blending function b of k comma d is defined over d sub intervals of the total range u starting at the not value u of k. Okay, so here we are considering what is my starting value, whether my starting value is 0, whether it is 1, whether it is 3, so that we are going to consider, and the blending function is defined over the d sub intervals of the total range of u. Okay, if my d is equal to 3, so I'm having the 3 sub intervals. Okay, still I reaches to the or whatever the range I'm having for the u, within that range I'm having the d sub intervals. Okay, let us understand the next property of the Bezier curve. The fourth property of the Bezier curve is the range of parameter u is divided. Okay, so what is the range of parameter is divided into n plus d. Okay, so depending upon the range of parameters u will be divided into n means number of control points and d plus d means number of sub intervals. Okay, definitely suppose I'm having the n value is equal to 3. I'm having 3 control points and I'm having 2 sub intervals. Okay, I'm having n value is equal to 3. I'm having 3 control points. Okay, and I'm having the sub intervals are 2. So there are the 3 control points and the 2 sub intervals. Then definitely I'm having the value of the u will ranges from, I consider it is from 1 to 3 plus 2 means 5. Okay, so I consider the n as my control point and d as the sub interval should be added. Okay, should be considered, okay, to get the correct shape of the B-spline curve. Okay, so these are the first 4 properties of the B-spline curve. Now let us understand it is having 3 more properties of the B-spline curve. Okay, so Bezier curve comparatively it is having only 3 to 4 properties, but we are having more properties of the B-spline curve, and the computation function is little bit complex as compared to the Bezier curve. Okay, but it is having the 2 advantages, so that's why we are considered that there is a trade-off between the advantages and the complexity of the B-spline curve. Okay, let us understand the next slide where we are having next 3 properties of the curve. Okay, definitely I think just now I have added over here the sub interval by n plus d sub interval by the n plus d value which is specified, okay, in the not vector. Okay, so I think there is no need we consider directly here the value, the range of u will be considered from n plus d sub intervals by the n plus d plus 1 value specified in the not vector. Okay, so no issue with this because we are already considering if I'm having n control point, the value will be n plus 1. So n will be always considered as n plus 1 because we should have the starting point and the end point should be minimum 2 value we have considered. Okay, so let us continue this discussion. Okay, so this is my the fifth property of the B-spline curve with not values labeled as z of 0. See, now I come to know that I'm having n plus d. Okay, I'm having n plus d plus 1. Why I have considered? Because I'm starting with the 0. Okay, so that's why we have considered it is n plus d plus 1. Okay, so with not values labeled as u0, u1, u2 up to un plus d. Okay, So suppose just now I have considered, suppose I am having n is equal to 3 and d is equal to 2, so 3 plus 2 5, so it is u5. This will be start from 0 1 2 up to u5, so that's why it is n plus d plus 1. The resulting B-spline curve, is defined only in the interval from naught value, okay, u of d minus 1 up to the naught value u of n plus 1. Okay, now here we have considered the naught value is my sub interval, okay, and my sub interval will be start from the u of d. Suppose d is equal to 2, so it will start from the d minus 1 means 1, so this is my starting point. It will become, so and it will be start from the naught value will start from, suppose the d is equal to 2, so 2 minus 1 means it will start from here u1 and up to the naught value u of n plus 1. Okay, so up to the n plus 1 value. So I'm having, this is 3 means I'm having u1 u2 u3, okay, and u4 up to it is having, and because this will becomes my last point, okay, so it will not considered in detail the first and the last point values or ending point values are not considered, comes under the not values. Okay, so that we have the, that is what the property we are having. Next property is each section of the spline curve, every section of the spline curve, that is between two successive not values. So the section between the two successive not values is influenced by the d control points. Obviously, it will influence by the number of sub intervals we are having, influenced by the d as a local control point that we are having. So each section of the spline curve between two successive not values is influenced by the d control point. Okay, so that we are considering. Okay. Now this is I consider as the last property of the B-spline curve. Okay, what is this last property? Says any one control point can affect the shape of at most d curve section. Okay, we are considering here any one control point can affect the shape. One control point is going to affect the shape at most d curve section. Okay, suppose I'm having for a one control point, I suppose I have divided it into two sub intervals, then it is going to affect. So one control point can affect the shape at most the d curve section. I'm having two sub intervals, so it is going to affect maximum the two sub intervals of that particular control point. Okay, so all these are the different properties of the B-spline curve. Okay, these are the different properties of the B-spline curve and that we have considered here. Okay, so let us continue our discussion with the help of the example, and we are considering the next part of the B-spline curve that will have a more focus on the use of the B-spline curve, how it will be represented, how this control function. I think we have seen that sub interval that we are having, what is the not value starting and ending point. Okay, now to understand all these things, I'm just moving to the next slide to continue our discussion. So now here, now I'm just focusing on the uniform periodic B-splines. Okay, so now we are focusing on the uniform periodic B-spline. So before going to this particular diagram, okay, let us understand the diagram shows the quadratic uniform, okay, B-spline blending functions generated for the curve with the four control points. Okay, so I'm having the number of control points. I'm considering here it as the four control points with the four control point that we are having. Okay, but here we have considered these are the periodic B-spline blending function. You can find maximum time we can consider as the periodic sinusoidal wave. Okay, so we are considering this is the periodic sine wave that we are having. So it is a periodic B-spline blending function for, you can find it here, n is equal to d is equal to 3. Means here I am having the n is also 3 and I am having the d is also 3 and a uniform integer not vector. Okay, so we are having the, it is a uniform integer not vector. Now my first diagram A, see you can find the exactly same similar shape is there. Okay, so it is, I have told that it is a periodic sine wave or sinusoidal wave that is generated or the signal is generated. It is having the four control points accordingly. So accordingly I am having this particular shape, okay, for the signal. But now you have to look at here, this is the axis. At this axis we are having, this is my u, okay, and here I am having the function blending function b. Here I am having this value 0 comma 3. Okay, I am having the value 0 comma 3. So here what this indicate, what is my starting value here? This indicate my starting value, okay, for the blending function is 0. Okay, starting point is 0. And what is my D? I am having the sub control point, it should be 3. Okay, so I am having minimum 3 control points here, 1 2 3. So obviously it is end with this particular value as a 3. These are the sub intervals that I am having, 1 2 and 3 sub intervals. That is my value of the D. So this is my starting point and I get this shape of something like this. Okay, now if I look at the diagram number B, I think the shape of the uniform periodic, okay, this is the periodic signal. Okay, this shows my periodic signal. Okay, but it is uniform, it is not going to change. Only what is going to change is my starting point of this, and number of interval D value I am again putting 3. So my D value is equal to 3, no issue with this. Okay, but my starting function value change. Suppose it is building function start from 1 comma 3. So I think you can find here the starting point is 1 and number of sub intervals are 3 that we are having. Okay, and it will end at this particular value 4. Okay, similarly here I am having the blending function 2 comma 3. So this is my 2 will be the k value will be 2. It will start from the 2, having number of interval will be 3. So this is 1 2 and 3. So here it is end. So similarly I am having this is value is 3 comma 3, starting not value or this value is 3, starting from the 3, and my again my number of intervals are 3. So this is first sub interval, second sub interval, and I get this is the another sub interval. So it is going to end it here. Okay, so this is a very simple example or simple understanding of the uniform periodic B-spline curves. Okay, how it will be drawn. Okay, so here we have to specify the value that we are considering, that is the k. I will consider it as a not value, which is starting from the, here it is starting from 0, it is starting from 1, starting from 2, starting from 3. Okay, here it is starting from 3 value, but I am having D is equal to 3. I am having this D, the maximum subinterval is 3. If I am having 4, I think I may have 0 1 2 3 and 4. The shape will be little bit different. Okay, so the shape may have changed. Okay, so this is what this particular diagram indicate regarding the uniform periodic B-spline curves. Okay, so we are having one more type of the curve that we are considering, not only periodic, uniform. We are having the periodic line, but it is not necessarily always uniform. It may be the cubic curve. I may want to have the B-spline curve which is cubic. Okay, so that's why I'm moving to the next slide now. Okay, now if we consider related to uniform periodic B-spline curve and the difference that we are having, we can also determine the parametric derivation at the starting and ending position of the curve. Okay, we can achieve this equation. So we can modify the shape of this in again in the uniform periodic B-spline, starting and ending position of the curve. How I can change this? Taking the derivation of blending function and substituting the endpoint values for the parameter u, we can find that. Okay, we can achieve this. See, what is I want to achieve here is the what is my starting point of the p start. Suppose I want p start should is be equal to p1 minus p0. Okay, I want the starting point should be not only p0, but it is the combination or the value p1 minus p0. Similarly, I want to change my ending function. So p dash end should be equal to, suppose I'm having the p3 value, p0, p1, p2, p3. So I get it not only ending point is not only 3, but it is p3 minus p2. Okay, I want to consider the both derivation of the blending function. So that is what we have mentioned. We can also determine the parametric derivatives at the starting and ending position of the curve. I want to change my blending function at the starting point and I want to change my derivative at the ending point of the curve. Okay, now the parametric slope of the curve, see this is very important. The parametric slope of the curve at the start position is parallel to the line joining the first two control points. Okay, so I'm not considering my starting point is only 1 as the p0, but I'm considering the p1 minus p0. So I also consider it will be start from this value and the parametric slope at the end of the curve. Okay, parametric slope at the end of the curve, okay, end of the curve is parallel to the line joining the last two control points. So because I have changed my function at the starting point and at the ending point of the curve. Okay, now due to this difference, how this my curve will look like? how my B-spline curve will look like. So let us understand this diagram. Okay, I want everybody to concentrate on the diagram. So this is quadratic periodic B-spline fitted to 4 control points in the XY plane. But now what is the difference I'm having? See here, I'm not mentioned the starting point is P0. Okay, so I have changed the derivative function, okay, at the starting point, as well as I have changed the derivative function at the end point, and I'm considering the difference of these two. Okay, means P1 minus P0. So somewhere the difference is coming. Suppose I consider it as here. So this is my starting point and this is my end point of the curve. The parameter slope of the curve, parametric slope of the curve will be changed. So here if I start from this point, it may have some different shape, but now I'm just changing the function at the starting as well as the ending. Okay, so this is what the difference. If it have started from P0 and end with the P3, I think the shape may be different. Okay, but now it has this particular shape because I have changed my starting parameter. Okay, so derivative at the starting and ending points of the curve had changed, and so it will not end at the P3 or it will not start at the P0, but it will start at the difference between P1 minus P0. Okay, so that is what we have written here. You can find it the difference here. This is P dash start is equal to P1 minus P0 and P dash end is equal to P3 minus P2. Okay, so P3 minus P2, whatever the difference I'm getting. So suppose it is at this particular point. So accordingly, the slope of the curve will be changed, and you can find I will get some different shape. I'm getting different shape of my B-spline curves. Okay, so this is what the another example. This thing which I cannot achieve. See, I cannot achieve this type of the shape or this type the curve in the Bezier, because in the Bezier I'm having the property it must start from the starting point or it must end at the ending point. So it must cover the start and end point. But this is not the case with the B-spline curve, and that is drawn, that is displayed with the help of this diagram, or that is shown with the help of this particular diagram, okay, of the B-spline curve. Okay, so let us continue our discussion to understand whether it is possible for me to have a closed B-spline curve. So can I achieve the closed B-spline curve here? Okay, so let us move to the next slide. So this is I'm having, it is now cubic, it is not uniform, but it is now the cubic periodic B-spline curve I'm having. Okay, since cubic periodic B-spline curve are commonly used in graphics packages, then periodic splines are particularly useful for generating certain closed curves. Okay, my aim is now to generate the closed curves, closed cubic spline curve I want to generate. Okay, for example, the closed curve as shown in the below diagram can be generated in sections by cyclically specifying the 4 of the 6 control points shown at the each step. Okay, so out of 6 control points, we are specifying the 4 point over there, and we are considering how I can achieve this, the closed curve, closed B-spline curve. If any 3 consecutive control points are identical, see this is very important, if any 3 consecutive control points are identical, the curve passes through that coordinate position. Okay, if 3 consecutive control points are identical, they are same, then definitely the curve passes through that coordinate position. Okay, and this is what is shown in the diagram. Okay, I want everyone to concentrate on the diagram. See, this is the example of my closed curve, closed B-spline curve. Okay, so here what is written, a closed periodic piecewise cubic B-spline constructed with the cyclic specification of the 6 control points. Okay, you can find out of these 6 control points, these are my 3 points. Okay, you are getting this, these are my 3 points. Here any 3 consecutive points are identical, they are more close to each other, automatically I get this particular shape. And here also I am having, okay, these are the 3 control points which are there, so automatically I get the shape of the B-spline curve, which is a closed curve. Okay, so I am getting this shape of the B-spline curve, and that is what is shown in this particular diagram. So it indicates the closed periodic piecewise cubic spline curve. Okay, so that is what we can achieve. We can achieve this type of the shape, okay, in the B-spline curve more easily as compared to the Bezier curve. Okay, so that's why we have discussed this particular point of the uniform periodic B-spline curve as well as the cubic B-spline periodic signal. And again, we have seen that how I can achieve this closed curve. Okay, to achieve the closed curve, I want any three consecutive control points should be identical. They should be more same. Okay, so I think by putting these three control points, okay, so I have achieved this. It will be considered to be more same. This is P0, this is P1, this is P2, this is P3, P4, P5, and automatically, okay, it ends with the P5 to P0. So automatically I will get this shape as the curve, which is a closed curve, okay, that we can achieve. Okay, now this is all about the discussion of the B-spline curve. Okay, but I just want to put one diagram or to show you one diagram how I can capture the picture or the aeroplane image with the help of the B-spline surfaces. B-spline curve we have learned, but I'm just putting one image related to B-spline curve also to end our discussion. So before ending the discussion, I want everyone to let us move to the last slide and understand one of the image. I think we have seen for the image which is captured, okay, in is similar to that of the Bezier splines. So formation of B-spline surface is same as the formation of the B-spline surfaces. Now the B-spline surfaces exhibit the same properties as those of their component of the B-spline curve. A surface can be constructed from selected values for parameters d1 and d2. Okay, so parameter, these are my d1 and d2, which define my subinterval, which determines the polynomial degree to be used, and from the specified knot vector. So that's why I told specifying this knot vector and specifying this value of d is important or additional thing in the B-spline curve, which will be help us to add the local control points over the spline. Okay, now we are just considering one diagram, okay, for our understanding to consider that how this will be, how this image is captured, or how I can achieve the surfaces with the help of the B-spline curve. Now the figure shows or the diagram shows an object, okay, which is modeled with the B-spline surfaces. Okay, this model, whatever diagram I'm showing, it is modeled with the help of the B-spline surfaces. Okay, so just look at this diagram. I can find it here, one aircraft or the helicopter is there, and it is related shape. You can find these are the shape, all the shapes of this, okay, different curves and the shapes, okay, that I'm having for this are captured with the help of the B-spline surfaces. Okay, I'm just reading the description of the diagram. A prototype helicopter designed and modeled by the Daniel Langlois of the Soft Image Incorporation. Okay, Soft Image Corporation. Okay, using 18000, means I think it is around 1,80,000 B-spline surface patches. I'm having here so many shapes which are combined. So how many shapes? There is 1,80,000 B-spline surface patches are there. So many things are connected with each other. Every shape is different. All are connected with each other. Okay, the scene was then rendered using the ray tracing, bump mapping, and reflection mapping. Okay, so this is what one of the diagram that we are considering. This object is modeled with the help of the so many B-spline surfaces. Okay, you can find whenever there is a curve, okay, all these curves in this diagram are achieved. So you can find the curve at this particular place, this everywhere you can find. This is also the curve that we are having. Okay, everywhere I can find this curve. Okay, everywhere I'm finding this curve, and all these curve and their surfaces are achieved with the help of the technique used by the B-spline surfaces. Okay, so this is what all about the understanding of the B-spline curves. I think we have seen at the in our today's session, starting with the what is the advantage of the B-spline curve. We have seen there are the two advantages of the B-spline curve as compared to the Bezier curve, but it is having the B-spline curves are little bit complex as compared to the Bezier curve. Then we have seen the how it will look like depending upon its values. Then we have seen the different properties of the B-spline curve. There are 7 properties of the Bezier curve, the B-spline curve that we have considered. Okay, and then we have considered the uniform periodic B-spline curve and its algorithm and its diagram. Then we have also seen the closed B-spline curve how will look like. and this is the last diagram which shows that the object which is rendered with the help of the or modeled with the help of the B-spline surfaces. Okay, this is all about the today's topic of discussion. So we are going to end our session here. Okay, I hope all of you have enjoyed understanding the B-spline curves. Okay, so thank you all the students. Thank you all.